PHA, an interconnected solution. I'm fairly certain everyone loves food, right? But what if I tell you every year in New Zealand 200,000 tonnes of food waste end up in landfill, costing about $1.17 billion. But the problem doesn't just end there. When all this food waste gets buried, it decomposes without oxygen, generating methane, a very harmful greenhouse gas. About 5.1% of New Zealand's greenhouse emissions are produced by waste, including food waste. Now, as Kiwis, I'm also fairly certain we all love our ocean, right? But what if I tell you every year in New Zealand 252,000 tonnes of plastic end up in landfill? But the problem doesn't just end there. All of this plastic never really stays in landfill. It travels to our oceans, causing serious problems like this, and this. Plastic also never really fully degrades. It leaves behind microplastics, which damages our waterways, species, and can even affect our health when we consume seafood. Both plastic pollution and food waste contribute to the climate crisis, our most pressing issue which everyone should be familiar with. So, as Kiwis, as much as we love food and our ocean, more importantly, it is our responsibility to be kaitiaki, guardians of the earth. Māori believe that there is a deep kinship between the tangata whenua and the environment. But how can we fulfill our roles as kaitiaki when two serious problems like this exist? As much as banning plastic sounds appealing, it's incredibly unrealistic. Our global plastic production has only increased exponentially, expecting to double by 2050. With a growing reliance on plastic in society, the ideal solution will provide a feasible alternative to plastic. But what if it could also reduce our food waste? Te ao Māori, the Māori worldview believes that everything in the world is interconnected. So following this philosophy, what if we can take two problems and solve it with just one solution? We can. PHA is a solution that can help solve both issues as it provides an alternative to plastic while using up excess food waste. PHA is a carbon-based polymer which can be used to create biodegradable bioplastics. Biodegradable plastics are plastics that decompose naturally in the environment, also known as being compostable. Thus, PHA has similar properties to regular plastic, but without the negative environmental consequences. It won't leave behind any hazardous byproducts or end products, such as microplastics. Studies shows that PHA can biodegrade within 2 months to 1 year in land or ocean. PHA is also considered a bioplastic because it's produced biologically by bacteria, as long as there is a carbon-rich source provided which the bacteria can feed on. There are many different types of PHA that can be produced. The specific type of PHA depends on the bacteria used and the carbon-rich source. PHA is no new concept. It has been around for ages, having been synthesized through monocrops like corn or sugar, which are both carbon-rich. However, this is unsustainable as such crops require large areas of arable land which is not only expensive to maintain but can lead to a loss of wildlife habitat. The cost of carbon-rich sources can be up to 50% of the production process. This large cost of production associated with maintaining a carbon-rich source for PHA is the main reason why it has not been wide-scale developed in the market, despite its environmentally friendly properties. However, food waste can provide a low-cost carbon-rich source for PHA production due to its widespread availability. Food waste is rich in sugar, starch, and protein, allowing for PHA to be produced from food waste in 5 main steps. Firstly, food waste would have to be collected from places like food industries, farms, and households, sorted into categories, then pre-treated into smaller components. Pre-treatment allows food waste to be broken down into PHA precursors. PHA precursors provide the carbon-rich conditions and compounds for bacteria to make PHA. There are many methods, but currently the best method to break down food waste is using enzymatic hydrolyzation, which uses water and enzymes. An enzyme is a protein which speeds up the reaction. It contains an active site which allows the substrate, the food waste molecule, to bind with the enzyme. This enzyme will then break the food waste molecule down with the help of water into smaller molecules such as sugar and fatty acids. These molecules produced are the carbon-rich PHA precursors. While this is proceeding, bacteria would have to be cultivated under specific conditions into a population capable of producing enough PHA. There are many different types of bacteria that can be used, such as C. necator and E. coli. Bacteria will then be harvested and fed with PHA precursors, which produce PHA as a storage product through a biosynthesis pathway. Studies show that the bacteria E. coli can produce PHA until it makes up 85% of its cell contents, whereas C. necator can produce up to 78% of its cell contents. Lastly, PHA is extracted from the bacteria and can be used to manufacture biodegradable plastic. This concept has been proven to be effective in multiple studies using different types of food waste and bacteria. Several companies have also started developing it for commercialization, which shows that food waste has the potential to develop PHA on an industrial scale. Producing PHA from food waste will bring many benefits to New Zealand's environment. Obviously, it uses up excess food waste, which means there'll be less greenhouse gases produced, which contributes to a better climate. However, more importantly, PHA will result in less plastic pollution as it biodegrades within 12 months and leaves no harmful consequences. There are also many economic benefits, as there will be less food waste, which can save up to $1.17 billion a year. PHA is also a product that has a lot of export potential. This is because PHA has various applications in agriculture and medical sectors, and can be also used for commercial packaging. PHA also has export potential as global demand for better alternatives to plastic is increasing due to the climate crisis. The government plans to phase out problem plastics and some single-use plastics by July 2025, which increases the likelihood for widespread commercialization of PHA, which not only further benefits the environment, but creates more jobs in the economy. This solution also follows the Waste Minimisation Act and helps with reaching our Zero Carbon Act. Plastic pollution and food waste are also social issues, as these problems will disadvantage certain communities. One of these communities is Māori, who own a significant proportion of assets in the primary sector, including 50% of the fishing quota, which is severely at risk from plastic pollution. By minimising plastic pollution through PHA, communities and industries that rely on the environment to support their livelihoods will be much better protected, improving order and financial stability. However, as with any new project, there are limitations and considerations. One of the limitations to consider is how food waste will be collected and the overall logistics associated with this process. Although food waste collected from industries and farms should be relatively simple, as these locations use limited food types, household collection will be the most difficult to sort. Fortunately, there are various groups that can help implement this process successfully. As food waste is involved, the advisory group, Māori Experts for Waste Minimisation, can help develop a national strategy for food waste collection. We can also take experience from local initiatives such as Pare Kore, a waste minimisation initiative implemented at Madai's and Māori organisations. Collaboration and the sharing of responsibility as kaitiaki is key. The overall cost of the large-scale process would also need to be considered. Fortunately, there is funding available, such as the Waste Minimisation Fund, which supports projects that increase the recycling of materials. However, It's also important to note that each food source has its own complexities and requires different pretreatments and bacteria. There is not a single solution to a specific type of food waste. Rather, there are multiple paths that could be taken, each with different pros and cons. The specifics of PHA production will have to be thoroughly researched and developed to make the commercialization of PHA a reality. However, the availability of various bacteria and food sources gives us the versatility to be innovative. Although PHA production may be difficult and expensive to implement initially, over time with more research and collaboration, this interconnected solution will greatly benefit New Zealand as it uses food waste to create a biodegradable plastic which reduces plastic pollution, helping to tackle climate change, an issue we should all be responsible for as kaitiaki. PHA production can also bring many environmental, economic, and social benefits to New Zealand. Ultimately, PHA provides Aotearoa with the capability to solve two major problems with one interconnected solution. Thank you.